In this video, we're going to look at triple integration with cylindrical and spherical coordinates. So we're going to do triple integration with cylindrical coordinates, and we'll do triple integration with spherical coordinates. Now, when we were in two dimensions, we had our regular rectangular coordinates, but we also could convert to polar coordinates using theta and r. And remember, the angle theta was the angle from the x-axis up, rotated counterclockwise. In rectangular coordinates, the point would have been an x value and then a y value. So in this case, our point in rectangular coordinates would have been the point 4, 3. In polar coordinates, we would have had this angle theta, and we would have had a radius which we called r. And we could have found r by doing r squared is equal to, in this case, 4 squared plus 3 squared. In this case, r would have been 5. And our theta we could have found by using this right triangle here. But let's pretend we didn't know this was 4 and we didn't know this one was 3. How could we convert using polar coordinates? Well, the x value is always going to be r times cosine theta. The y value is always going to be r times sine theta. If you're trying to find the r and you know x and y, then x squared plus y squared is equal to r squared because of the Pythagorean theorem and the right triangle. And then tangent of theta was y over x. The other thing we saw when we switched from integrating with rectangular to integrating with polar coordinates over a region in the xy plane. Well, if we just did rectangular, we could do dx dv. But when we do polar, we have to put in this additional r. So we get r dr d theta when we integrate over the xy plane, some region in the xy plane, I should say. So when we did double integration with polar, we put in r times dr d theta. Well, if we extend the idea of polar coordinates into R3 by just adding a third variable z, then that's what cylindrical coordinates are. So the rectangular coordinates x, y, z, the rectangular coordinates in 3 dimensions are x, y, and z. The cylindrical coordinates will be r, theta, and z. So if we're willing to deal with polar coordinates and extend those into 3 dimensions by just adding the variable z, then we get cylindrical coordinates. And these are called cylindrical coordinates because if you think of the r and theta, they give you the polar on the xy axis, and then you extend to z. If I let r be constant and theta go all the way around, I get a circle. If I extend that using z, I end up getting cylinders. So these are cylindrical coordinates. Again, just polar coordinates projected onto 3 dimensions by adding a z. So all of our standard conversions will be there. X is going to be r times cosine theta. Y is going to be r times sine theta. r squared is going to be x squared plus y squared. Tangent of theta is going to be y over x. And the z in both cases is just the same. So here we have rectangular in 3 dimensions, and we can convert into cylindrical in 3 dimensions. And again, this is just like polar in 2 dimensions versus rectangular in 2 dimensions. So let's do a couple of examples here, going from rectangular points to cylindrical points. We have the rectangular point 4, 3, 5, and the rectangular point -2, -1, 6. And we want to find the corresponding cylindrical point. So here's what we'll see. The rectangular point 4, 3, 5 converts to the cylindrical point. Well, r is going to be such that r squared is equal to x squared plus y squared. In this case, x squared is 4 squared, y squared is 3 squared. So when we do r theta z, that is the same thing as doing, well, we'll take this positive square root of 4 squared plus 3 squared. That's, again, r squared is x squared plus y squared. So if I take this positive square root, I'll get a positive r. Theta is such that tangent of theta, I probably should have done this, r. So let's say r squared is equal to 4 squared plus 3 squared, which is equal to 25. So r is going to be 5. I'll just write it here that way. That's probably easier to see. Theta is such that tangent of theta is y over x. So that is 4 over, assuming, no, not 4, 3 over 4, excuse me. And so I can take inverse tangent of 3/4, and I get in radians about 0.6435 radians. That's what my theta is. Or if you wanted to, you could write that as tangent inverse of 3/4 if you wanted an exact answer. Okay. And then lastly, the z value for rectangular is the z value for cylindrical. So we get 5 in both cases. So this is the point 5. Again, inverse tangent of 3/4, which is approximately 0.6. I'll just round it to 2 decimal places, about 0.64 and then 5. So that's the cylindrical point. Now, if you do the same thing here, you have to be a little bit careful. My r, well, let's go through this. R squared is going to be x squared plus y squared. Negative 2 squared is 4. Negative 1 squared is 1. So we get an r, which is the square root of 5. So that's my r. My theta, I have to be kind of careful of because I know that tangent of theta is equal to negative 1 over negative 2. However, the way that inverse tangent works on most all calculators is that inverse tangent is going to give me the angle that is in the first quadrant in the xy plane. Negative 2, negative 1 in the xy plane is in the third quadrant. So I'm going to actually have to add pi to that in order to get the proper angle. So again, inverse tangent always gives you out an angle between negative pi over 2 and positive pi over 2. So in the first and fourth quadrants. Therefore, if you're given a point in either quadrant 2 or quadrant 3 in the xy plane, again, I'm just talking about the first two coordinates here, then I have to add pi to that. So pi plus inverse tangent of 1/2 is my angle. Hmm. Inverse tangent of 1/2. Excuse me. Okay. And then as always, the z value just transfers over. So the z value is 6. And if you want an approximate answer, obviously we have square root of 5, which is about 2.24. If I take pi plus the inverse tangent of 1/2, I get about 3.61. And then 6 is my z value. So that is the cylindrical coordinates for these 2 points. And the key thing here was how we got that theta, remember? So in the xy axis, in the xy plane, excuse me, in the xy plane, if we're in the first or the fourth quadrant, then we can just use inverse tan. If we're in the second or third quadrant, we have to do pi plus inverse tan. So now let's do conversions in the other direction. Let's say we have cylindrical coordinates of cylindrical points of 4 pi over 3 negative 5, and also 6, 7 pi over 3, 2. And let's convert those to rectangular form. All right, so in rectangular form, first of all, we should know that x is equal to r times cosine of theta, and y is equal to r times sine of theta. So, oops, r times sine of theta. So when we go to find our rectangular coordinates, all we have to do is take 4 times cosine of pi over 3. You can type that in. Now, I didn't mention this earlier, but make sure that we're in radian mode, obviously. That's a 2 for your x value, 4 times cosine of pi over 3. If I take 4 times sine of pi over 3, I get about 3.46, which is 2 times the square root of 3. And then the z value is still -5. Okay. You can calculate 2 times the square root of 3 if you want to get an approximate value, if that's something you're interested in. In terms of this second point, 6 times cosine of 7 pi over 3. I haven't typed that one in yet. I just get a 3 there. And then when I take 6 times sine of 7 pi over 3, I get negative, oh, excuse me, I get 3 root 3. And then the z value turns into a 2. By the way, you might say, why did we get the same thing? Why did we get, well, 7 pi over 3? If you think about going around the unit circle, 7 pi over 3 is more than 2 pi. So 7 pi over 3 is the same thing as pi over 3. So very similar things. But doesn't matter what you put in there. We would still have interesting rectangular coordinates. By the way, obviously these 2 points were in the XY system, would have both been in the first quadrant in the XY plane. But even if they're not in the first quadrant on the XY plane, we still just plug in r times cosine theta, r times sine theta. So that's how we go from cylindrical to rectangular. There's a little bit less work than going from rectangular to cylindrical. That getting the theta when you go to cylindrical does take a little bit of knowledge of how your inverse tangent works. Now, we're not looking at cylindrical coordinates just so that we can convert points back and forth. We're looking at cylindrical coordinates to help us with triple integration. And essentially, if we have a function w equals h of r theta z, so if we have a function written in cylindrical coordinates, when we do a triple integration around a 3-dimensional object with respect to volume, we will set up that system, and just like when we converted from rectangular to polar, we have to include a times r dr d theta. So if we have a z, we'll do r times dz dr d theta. Now the order of the integration, whether it's z, then r, then theta, we can flip those around sometimes depending on what our functions are. If our functions go from z equals this to z equals that, and then r equals this to r equals that, and then theta equals this to theta equals that, then we integrate with respect to z, with respect to r, with respect to theta. But a lot of times we'll see the z is going to be numerical bounds, the r might be some numerical bounds, the theta might be some numerical bounds, and so we have play with which one we integrate with first. But the whole thing relies on, if we're taking and integrating with respect to volume, then we have to include an r dr d theta dz. So including this r is the big takeaway. So let's do one where we do a triple integral in cylindrical coordinates, and then we'll describe what we've found. We'll describe the region in space, and we will calculate the integral. So we're going to integrate with respect to z first, from 0 to 3, with respect to theta next, from 0 to pi over 2, and with respect to r, from 0 to 6. And we have an r in here. So this would be like we were doing a triple integration of 1 dv, which is kind of like finding volume. So our function here would have been like a 1. So pretend we're essentially finding volume of whatever this three-dimensional object is. All right, so let's go ahead and do the integration first. All right, so let's take a look at this. It's a pretty straightforward integration. So we're integrating from 0 to 6, and then we're integrating from 0 up to pi over 2. And this inside integration, r is a constant. So when we integrate with respect to z from 0 to 3, we just get 3 times r. So we get 3r. Oops. D theta dr. When we integrate with respect to theta, again, r is a constant, so is 3. So integrating from 0 to pi over 2 of 3r is going to give me 3 pi over 2 times r. And then we're going to integrate with respect to r from 0 to 6. Now, if you integrate from 0 to 6, 3 pi over 2 r, with respect to r, from 0 to 6, you end up getting 27 times pi. And so this triple integration is 27 pi. Now, like I said, if you think about it, this is some sort of integration of essentially 1 dV, okay? Because when I change the 1 times dV, I get R times dz, d theta, dr. So this is the volume of the object described by these bounds. And the object described by these bounds has z going from 0 to 3, theta going from 0 to pi over 2, and r going from 0 to 6. So what that is, think of the theta first. The theta going from 0 to pi over 2 gives you a quarter in the first quadrant. R going from 0 to 6 is giving you a circle of radius 6. So we're getting a quarter of the circle of radius 6 in the first quadrant. And then we let z go from 0 to 3. So we basically get a quarter of a cylinder. If this went from all the way from 0 to 2 pi, we'd get the entire cylinder. But we get a quarter of a cylinder. That cylinder has radius 6 and height of 3. Let me graph that out. Now, when you do this on this Desmos graphing device, it doesn't like me in the 3-dimensional graphing device using R's and thetas. So I had to graph it in a different way, but this is what's going on. So if you think about the R going from 0 to 6 and the theta going from 0 to pi over 2, we get essentially the cross-section, the portion of a circle in the XY plane. And then we let the z go from 0 to 3. So we get a quarter of a cylinder in 3-dimensional space. That's our d that we're integrating over. And it said that, again, the volume of this object happens to be 27 pi. So that's the object that we're looking at. R from 0 to 6, theta from 0 to pi over 2, and then z from 0 to 3. So quarter of a cylinder. And you can see why this is called cylindrical coordinates. If I don't limit myself to just the first quadrant, then I'm getting cylinders a lot of times. But there you go. So this is the quarter of a cylinder that we integrated. And we integrated, the integration happened to line up with the volume of this object. I did that on purpose, obviously, but anytime you do a triple integration, it doesn't always have to give you a value. It could give you some other things if your function were different, meaning if the w equals h function is giving you something else. So in terms of this function here, if the h is just the constant of 1, I get value. If it's something else, I get something else. All right, so let's do another example. 1.5 inch Schedule 40 PVC pipe has an outside diameter of about 1.9 inches and an inside diameter of about 1.61 inches. Let's ask, what is the volume of a 6-inch length of 1.5-inch Schedule 40 PVC pipe. Now, pipe is obviously cylindrical shape, and if we want to find volume, we'll use um, 1 as the function we're integrating. But the key thing here is that Schedule 40 PVC pipe is a cylinder, but it's hollow in the middle. And so if we're going to figure out the volume of the actual substance that makes this up, we don't want to include the middle portion. And so there's a really straightforward, nice way to integrate this using cylindrical coordinates. Let's go ahead and do that. Now, before we set up our triple integration with cylindrical coordinates, I want to point out that we're talking about a pipe here with a hollow center, but we do have some thickness here. The inside, oh, you know what? This is diameter. I apologize. And I wrote this in terms of radius instead of diameter. Schedule 40 diameter has an inside diameter of 1.61. That's the distance all the way across. I miswrote this. I apologize. That means the radius should be half of that, so 0.805. And the diameter of the Schedule 40 pipe is on the outside is 1.9. So that means the radius is 0.95. So the pipe looks like this. And we're trying to find the volume of a 6-inch length of that pipe. Try to do 6-inch length. Yeah, so a 6-inch length of that pipe. Okay. So if you think about integrating in cylindrical coordinates, I can start my integration with r at the radius of 0.805 and go out to the radius of 0.95. My theta is going to go all the way around because the pipe makes a complete circle. And then the z value, obviously, is 6 inches, so we're going to go from 0 up to 6. But that's the whole integration. Let's go ahead and do that. So 1.5-inch has an outside diameter of 1.9, inside diameter of 1.6. I'm going to say outside radius is 0.95 inches and inside radius is 0.805 inches. Okay. So if we want to integrate with respect to z, with respect to theta, with respect to r, z is going to go from 0 to 6. Theta is going to go from 0 to 2 pi. And r is going to go from 0.805 to 0.95. Notice how all of these are numerical bounds. So if I wanted to switch up my integration, I'm free to do so. And I'm going to do that. So in other words, if I want to integrate with respect to r first, and then with respect to z last, I can do that. so long as I switch up the numerical values on the integration. So if I want to go R first, then R goes from 0.805 to 0.95, Z last, 0 to 6. I think this is how I will integrate. So if we integrate this, this R, integrating R with respect to R from 0.805 to 0.95 gives me a ugly looking decimal, but that's perfectly acceptable to have an ugly looking decimal. It is 0.1272375. I'm going to integrate that with respect to theta, and then integrate that with respect to z. If I integrate this with respect to theta, I'm just going to multiply by 2 pi. And then if I integrate with respect to z, I'm going to essentially multiply by 6. So if I take that number, 0.1272375, and I multiply by 2 pi, I end up getting 0.254475 times pi. And then if I multiply by 6, I get 1.52685 multiplied times pi. So the volume is right about 4.80 cubic inches. All right. Again, all of my measurements here were in inches. So about 4.80 inches, cubic inches, excuse me. So that's the volume of a 6-inch length of Schedule 40 PVC that is 1.5 inch Schedule 40 PVC. All right. So that can find the volume. So in cylindrical coordinates, that's a really straightforward calculation. If we were trying to do this in rectangular coordinates, it would have been much more difficult. Let's do another example here. Let's use integration with cylindrical coordinates to find the center of mass of a three-dimensional annulus bounded by x squared plus y squared equals 25, x squared plus y squared equals 49, z equals 0, and z equals 4. So basically, we want to take the ring, which is in between the circle of radius 5 and the circle of radius 7, from z value of 0 to z value of 4, with this density function. The density function is going to be 1/2 z. So hopefully we can envision this in our mind. I will graph a picture real quick, but hopefully we can envision that in our mind. It's the annulus between circle of radius 5, circle of radius 7, and z values from 0 to 4. So I've graphed that here. Again, circle of radius 5, circle of radius 7. So in between the cylinders from z equals 0 to z equals 4. And you can imagine that that's the center of mass of a ring. Although remember, our density function is not constant here. Our density function was 1/2 z. So as we get taller, the thing gets denser. Now, anytime we're finding a center of mass, remember that if you're looking to calculate the mass, we're going to do a triple integration of our density function. Usually that's denoted by delta. And the way that we looked at the density function, our density function was written in terms of x, y, and z. Now, when we convert to cylindrical coordinates, we are going to have to, well, if our density function has x's and y's in it, then what we'll do is we'll convert those x's and y's into cylindrical formats. The z's don't matter too much. And then we'll convert this dv to an r, dz, d theta, dr. Again, it's not going to matter too much on the bounds. I think I'll do the z last. So I'll integrate with respect to z last. And remember, z goes from 0 to 4. And if I integrate with respect to theta second, theta is going to go from 0 to 2 pi. And then if I integrate with respect to r first, r in this case goes from radius 5 to radius 7. My density function is 1/2 z. And then I do an r, dr, d theta, dz. Now, with respect to r, z is a constant, so I can kind of pull that through if I want to. And what's going to happen is that the mass is integrate from 0 to 4, integrate from 0 to 2 pi, excuse me. When I integrate 1/2 r from 5 to 7 with respect to r, I end up getting a 6. So I get 6z d theta dz. When I integrate with respect to theta, the z is a constant, so I just end up multiplying by 2 pi. Keep putting the wrong thing. And when I multiply by 2 pi, I get 12 pi times z dz. So I'm integrating 12 pi z with respect to z from 0 to 4. And obviously, I can type that into the calculator. I can pull pi out if I want. I end up with 96 pi as my final mass. Now, our center of mass, we usually write in rectangular coordinates, so I'm going to do that as well. Our center of mass, we're going to, now we have the mass of 96 pi. Let's do a center of mass. The moment from the YZ plane is going to be an x multiplied times my density function. And when we do that, and when we convert We're going to put an extra x in here, but because we're using cylindrical coordinates, we know x is r times cosine of theta. So this x becomes r cosine theta. We'll be integrating with respect to r, with respect to theta, with respect to z. Now I'm going to do a little trick because I know kind of how this is going to turn out. I'm going to integrate that same thing, but in a different order. We have r squared times z times cosine of theta. And right now we're integrating with respect to r first. I'm going to integrate with respect to theta first. And then I'll do z, and then I'll do r. So if I go with respect to theta first, I'm going to go from 0 to 2 pi. And then z goes from 0 to 4. And then r goes from 5 to 7. Now, the reason I do this is because I kind of know what's going to happen. So I'm going to integrate this 1/2 r squared z is just a constant with respect to theta. And if I integrate cosine of theta with respect to theta from 0 to 2 pi, it turns out I get a 0. And so everything inside there is going to turn into a 0. This times 0 is just 0. And then when you integrate 0 from 0 to 4, you get 0. And then integrate 0 from 5 to 7, you get 0. So because I kind of knew what was going to happen, being able to integrate with respect to theta first really helped me in the sense that it simplified everything that I could do and made everything 0 because of that integration of cosine from 0 to 2 pi. Now let's look at the other moments. The moment from the xz plane is going to be similar. I'm going to take y times the density function. Oops. So y times 1/2 z. And then the dv turns into r, dr, d theta, dz. But again, z is constant. The y I have to change to r times sine of theta. And once again, I'm going to do the same thing I did up here. I kind of know how this is going to work now. I'm going to integrate, this is r times r, we got a z, and then we have sine of theta. We're going to be integrating with respect to theta from 0 to 2 pi. And if I integrate sine from 0 to 2 pi, I get 0. And so everything just turns into 0 once again. Hopefully that's not too much. Now my last moment is going to be the moment from the XY axis. And in that one, I have to multiply times a Z. That's pretty straightforward though. When I plug in, so I go 1/2 Z times Z, that's 1/2 Z squared. So when I take Z times my density function, I get 1/2 Z squared. The dV turns into an R, dr, d theta, dz. Integrating 1/2 Z squared from 5 to 7 will give me 6. So I'm ending up with a double integration from 0 to 4. So that is a Z value from 0 to 4. And then a theta value from 0 to 2 pi. When I integrate 1/2 Z squared R with respect to R, excuse me. So when we do R, 1/2 R with respect to R, we get 6. The Z squared is just a constant. So I get 6Z squared d theta dz. Once again, with respect to theta, 6Z squared is a constant. So what's going to happen is you're just going to multiply that by 2 pi. So you get 12 pi times Z squared integrated with respect to Z. And when I do that integration, I end up with 256 times pi. So now I've done 3 integrations using cylindrical coordinates, and now I can find my center of mass. Remember the center of mass? We take the moment about the YZ from the YZ plane, divide it by mass. That'll give me my X value. The moment from the XZ plane, divide that by mass. That'll give me my Y value. The moment from the XY plane divided by mass will give me the Z value. In this case, that's 0 over 96 pi, comma, 0 over 96 pi, comma, 256 pi divided by 96 pi. So the center of mass is 0, 0, and then 256 over 96 is 2 2/3. Or 2.67. So that's the center of mass of that object. Again, the density function was 1/2 Z. So it's not exactly the center of that object, but it shifted up a little bit because as we shift up, as we increase our Z value, the object gets more dense. Hopefully that makes sense. So we can see the center of mass right there. Okay. Again, it's equally dense in the Y and X directions, but it's not perfectly in the middle here. It's a little bit higher because this object is a little bit denser as you increase Z values. So there you go. That's the center of mass of this annulus with the density function 1/2 Z. Now the next system that we're going to use is going to be nice when we're integrating objects that are spheres. And so this is called spherical coordinate system. Cylindrical coordinate system is really nice when we're dealing with cylinders. Spherical coordinate system is really nice when we're dealing with spheres, obviously. Now, the spherical coordinate system is going to use two angles and a distance. And those two angles and a distance is going to generate coordinates in R3. Now the distance here is going to be the distance from the origin. And we always call that rho. That's kind of like the Greek R. So this is the Greek letter rho. And that's going to give you the distance from the origin in a straight line to the point in R3. So the point in three-dimensional space. Now, what two angles are we going to use for reference? The first angle that we're going to use is the angle from the x-axis in the xy plane. That is theta. So this is the same theta that we use in polar coordinates. So we go how far from the x-axis in the xy plane. Now the second angle we're going to use is going to be the angle from the z-axis in any direction, but it's going to be down from the z-axis. So the positive orientation of the z-axis is going to be the initial ray, and then we're going to move down in any direction from that z-axis. And that angle we call phi. Usually it's this symbol. There's actually different phi symbols, but we'll use this symbol for phi. It kind of looks like a loop. So you kind of draw down, go up, loop. That's the Greek letter phi. Okay, so we have theta, which is the same theta we had in polar coordinates. We have phi, which is an angle from the z-axis. And we have rho, which is our distance from the origin. If we look at a picture, I didn't draw it perfectly, but let's say we have a point in three-dimensional space up here. What we're going to do is we're going to get an angle in the xy plane. That's our theta. Our rho is going to be a straight shot from the origin to the point. That distance gives me the rho. Theta is from the x-axis. And then we hinge down to get the phi. So the phi is coming from hinging down from the z-axis. Again, kind of hard to see, but hopefully this picture does it justice. Now that means we're going to have some different conversions when we do this. Oh, by the way, usually the ordering is always rho, theta, phi. So rho, theta, phi is the order of a point in spherical coordinates. So we're always doing rho first, and then theta, and then phi. When we go to integrate, you can integrate in any way, but the point is always rho, theta, phi. Just like the point in rectangular coordinates is always x, y, z, and in cylindrical coordinates, it's always r, theta, z. In spherical, it's always rho, theta, phi. Now, when we're going from rectangular to spherical, we're going to have a couple of, well, we're going to have a lot of different conversion formulas. First off, rho is the straight distance from the origin to the point. So if we have a point which is x, y, z in rectangular, then rho squared is going to be x squared plus y squared plus z squared. Notice that x squared plus y squared plus z squared equals a number is an equation for a sphere in three-dimensional space. So if you have x, y, and z, then you can find your rho by doing x squared plus y squared plus z squared is equal to rho squared. In terms of if I want to find tangent given the x, y, and z, well, tangent of theta given x, y, and z, tangent of theta is y over x, just like it was in polar coordinates. And then what is this phi? How do I find it? Well, cosine of phi is going to be z over the square root of x squared plus y squared plus z squared, which, if you think about it, that's just z over rho. Okay? So normally we think of that as z over rho. But if you want to think of it in terms of x, y, and z, it's z over the square root of x squared plus y squared plus z squared. This cosine of phi just comes from SOHCAHTOA. This is the cosine is adjacent over hypotenuse. And so if you look back on that triangle, this triangle, the phi is the same here as this one. So phi looks like that, but it's also the angle of this right triangle here. The hypotenuse of that right triangle is rho, and the adjacent, this is the z value here, the height of your point. So cosine of phi is z over rho. Now, if we have spherical coordinates and we want to get to x, then we do a very similar thing that we did in polar and in cylindrical. X is going to be rho times sine of phi times cosine of theta. It's not just rho of times cosine of theta because now our rho is in three-dimensional space. So I have to do rho times sine phi times cosine theta. And then y is going to be equal to rho times sine of phi times sine of theta. And then z is going to be rho times cosine of phi. By the way, this is the same equation as this one. Remember, this is z over rho is equal to cosine of phi. If I just divided both sides by rho, I'd get that exact same equation. So if we want to go from rectangular to spherical, I can use these three. If I want to go from spherical to rectangular, I can use these three. Now, what about going back and forth between cylindrical and spherical points? Well, theta is the same in both. So theta in the cylindrical and theta in the spherical are exactly the same. And then the R value in cylindrical is actually rho times sine phi. The Z value in cylindrical is rho times cosine of phi. Rho squared is equal to R squared plus Z squared. This is probably a better way of thinking of it than easier to see anyways than with our rectangular, because this shows us that the triangle we drew has a hypotenuse of rho and legs of R and Z. The other conversion formula that we have is that tangent of phi is equal to R over Z. Again, this comes from this right triangle with two legs of R and Z and hypotenuse of rho. So if you look at this triangle, this length here in the XY plane is actually our length R. And this is the height. So this is Z. So this is R, this is Z, and obviously our theta, phi here. The angle here, the angle here on this right triangle is going to also be phi, just like this was. So that's also going to be phi. But the legs of the right triangle are R and Z with hypotenuse rho. And if you think about that, that's where all of these conversions are coming from. I won't spend a lot of time going through that, but that's what's happening. So let's do some conversions. We're going to take the rectangular points we saw before, 4, 3, 5, and -2, -1, 5, and we're going to convert those to spherical. And then we're also going to take some cylindrical points, 4 pi over 3, -5, 6, 7 pi over 3, 2, and we'll convert those to spherical as well. Then we'll take a couple of spherical points, 2 pi over 3, 3 pi over 4, and we'll convert those to both cylindrical and spherical. And we'll also do the same thing for 0.5, 7 pi over 6, pi over 4. Remember, in the spherical system, we always do rho, theta, phi. In the cylindrical system, it's always R, theta, Z. And in the rectangular system, it's always X, Y, and Z. So we'll do all of those conversions right now. Okay, so rectangular points 4, 3, 5. We want to convert that to spherical. And the first thing we're going to do is find our rho. So rho squared is equal to x squared plus y squared plus z squared. I'm getting that from this conversion formula here. And so the spherical point is going to have a rho of the square root of 16 plus 9 plus 25. So that's the square root of 50. So that's my rho. When I want to go find theta, well, once again, I realize that theta in the XY plane, where should it be in terms of quadrants in the XY plane? Well, it should be in the first quadrant, so I can just take the inverse tangent. So in other words, if I want to find theta, that's going to be the inverse tangent of y over x, so that's 3/4, which is about 0.64. And I'm just going to make an approximate theta there. So my theta is about 0.64. I'll do an approximate version of both theta and phi. And then lastly, my phi, which again, there's multiple ways to write phi or to draw the letter phi. I'm using this one because that's what the book does. We do cosine of phi is equal to z over rho. And since I already know rho is square root of 50, I'm just going to take 5 over square root of 50. So it's going to be cosine inverse of 5 over square root of 50. By the way, cosine inverse gives me back values from 0 to pi. And so I have to be a little bit careful of what's going on here. My point is it has all positive values. So it is the phi, which is just cosine inverse of 5 over square root of 50. Hopefully that makes sense. In other words, you get about 0.79. I should have said approximately. There we go. All right. So you can do, in other words, you can do the same thing if you should have done a, let me just say this, okay? Phi goes from 0 to pi. If we do the difficult work of quadrants with theta, then we can always assume that our phi goes from 0 to pi, and we'll be all right. Okay? So I don't necessarily have to worry about quadrants when I get to phi, as long as I worry about quadrants when I'm at theta. So that's kind of how that works. Let's do the next one here. The next one, I'm just going to kind of state where I'm getting this. Rho squared is equal to -2 squared plus 1 squared plus 5 squared. So rho is squared is going to be 30. And so rho is going to be the square root of 30. Did it just like this. Theta is going to be the inverse tangent of -1 over 2, which is the same thing at -1 over -2, which is the same thing as 1 over 2. But because The XY coordinates give me quadrant 3. I'm going to add pi to that. And so if I take the inverse tangent of 1/2 plus pi, I get about 3.61. And then because I did the hard work of quadrants here, I don't have to do the hard work of quadrants when I calculate my phi. I just have to take the cosine inverse of z divided by rho. So that is cosine inverse of 5 over the square root of 30, which gives me approximately 0.42. Now I'm using decimals because these are not really nice angles that we're dealing with here, but you can see the idea of where we're going. So as long as we take care of quadrants using the theta, the phi is going to take care of itself. All right, so here's what I mean by that statement, okay? I have written here a point essentially in polar coordinates, although I'm using A's and B's instead of phi's and thetas. So in terms of the angle here, the angle A, oh, I think I have this backwards here. Hold up. Excuse me. No, I did have it right. So the angle A is my phi. Now it's kind of hard to see, but when angle A is 0, then we are parallel with the z-axis. And as we start growing, obviously it's going down and down and down, and something weird happens right there. So my apologies. I did have that goofy. So anyways, let's look at A. As A starts at 0, we goes all the way down. When it hits pi, we're again parallel with the z-axis, but we're pointing down. Now, if you go beyond pi, then you're going to go back up, and we're going to get into the other octants, the other 8 regions in R3. But I could have just as easily, instead of using this phi that's beyond pi, I could have used a smaller angle and then rotated it around utilizing theta. So if I wanted to be in this octant over here, I could have used a phi value from 0 to pi and then just arranged my theta. My theta takes and circles around the XY plane, makes a circle, sweeps like a circle in the XY plane. My R would extend that out. Right now, I've just set my R as 3 so we can see it. But there you go. So if we have two angles that are both 0, then we're right along the z-axis. My phi, as phi increases, we move down. Once we get to pi, we can stop because if we wanted to get down there, all we'd have to do is rotate it around in a circle. Rotate around in a circle. So if I take care of the correct quadrant when I use theta, then I can always assume my phi is between 0 and pi. And therefore, I can always use the phi that I get when I just do cosine inverse of z over rho. Okay, let's convert from cylindrical to spherical next. Here we have 4 pi over 3 negative 5. In the spherical points, we're going to do rho and then theta and then phi. Well, theta here is pi over 3. It's the same theta that we had last time. And our phi, well, we'll have to calculate that. So if we're going from cylindrical to spherical, I go back and reference these. Rho squared is equal to r squared plus z squared. And tangent of phi is r over z. So let's start with this one. Tangent of phi. Oh, that's what I said. There's more than one way to write phi. Tangent of phi is going to be r over z. That is 4 over negative 5. So if I do the inverse tangent of 4, excuse me, divided by negative 5, I get a negative 0.67 for my phi, roughly. Now you might say, wait a second, in previous cosine inverse gave me back a phi between 0 and pi, but tangent inverse is going to give me back a phi between negative pi over 2 and positive pi over 2. But again, that's perfectly fine because we're taking care of the quadrants and octants using our theta again. We just have different bounds on what phi can be when I use tangent versus when I use cosine. And then my rho, like we said, rho squared is equal to r squared plus z squared. So r is 4, z is negative 5, so that's 16 plus 25. So rho is going to be the square root of 41. Okay. If you didn't follow that, basically rho squared is equal to 4 squared plus negative 5 squared. All right, let's do the same for this one. 6, 7 pi over 3, 2. In spherical coordinates, we're going to have a rho, a theta. Theta is 7 pi over 3 in spherical, just like it is in cylindrical, and then a phi. So there's our phi symbol that we use. All right, once again, tangent of phi. Keep wanting to do that. Tangent of phi is going to be equal to, in this case, r over z is 6 over 2. Which gives you a phi of about 1.25. And the rho, not sure what's going on there. The rho is what we get when we take rho squared is equal to r squared plus z squared. R squared is 36. Z squared is 4. So rho in this case is going to be the square root of 40. So that's what we get as far as that's happening. That's our point. So lastly, let's go to spherical and converting from spherical to cylindrical and from spherical to rectangular as well. This one's a little bit more straightforward because of the way the conversions go. So I pulled up the x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. And then with cylindrical, it's r equals rho sine phi, z equals rho cosine phi. And so if we're doing cylindrical coordinates, the r is going to be 2 times sine of phi. Just remember, phi in this case is 3 pi over 4. So 2 times sine of 3 pi over 4. I get about 1.41. So about an r of about 1.41. I'm going to give decimal versions of this answer. In cylindrical coordinates, the theta is still pi over 3. And then the z is going to be rho times cosine of phi. So that is going to be 2 times cosine of 3 pi over 4, which is about negative 1.41. So a little bit quicker going from spherical to cylindrical because the conversions are a little bit easier to deal with. Not super quick, but still. Now, if I want to, I could take from cylindrical to rectangular, but we're going to go straight from spherical to rectangular using these. So x is 2 times sine of 3 pi over 4 multiplied times cosine of pi over 3. That is rho times sine phi times cosine pi over 3. And in rectangular, I get about 0.71. By the way, that's actually square root of 2 over 2. Now, the y value is going to be 2 times sine of 3 pi over 4 times sine of pi over 3. When all of that is plugged in, you should get about 1.22. And the z value is going to be rho times cosine of phi. Rho cosine of phi. Z value is the same in both cases. And so you're going to end up with a negative 1.41 when that's calculated. Now, in this case, in the other point, 5, 7 pi over 6, pi over 4, the R value is going to be rho times sine phi. That is 5 times sine of pi over 4. That's about 3.54. Theta is the same theta, so that's 7 pi over 6. And z is going to be 5 times cosine of pi over 4. And 5 times cosine of pi over 4 is also about 3.54. If you want to use square roots, square root of 2, that is perfectly okay. You can get an exact answer by knowing that sine of pi over 4 and cosine of pi over 4 are both root 2 over 2. I'm not going to do that right now, though. All right, let's go to rectangular. So with rectangular, it is 5 times sine of pi over 4 multiplied times cosine of 7 pi over 6. When I do that, I get a rectangular value of x as negative 3.06, roughly speaking. My y value is going to be 5 times sine of pi over 4 times sine of 7 pi over 6. And I get approximately negative 1.77 for my y value. And then the z value, once again, is going to be 5 times cosine of pi over 4, which is approximately 3.54. So we can use these formulas, these conversion formulas, to go from spherical to cylindrical to rectangular, to go from rectangular to spherical, to go from cylindrical to spherical. Now, we didn't bring up spherical coordinates so that we can convert points. We are looking at spherical coordinates so that we can integrate using spherical coordinates. So how do we do triple integration with spherical coordinates? Excuse me. There, spherical coordinates. So let's say we have a function given spherical coordinates, written in with spherical coordinates on a closed bounded region D in space. If I want to do a triple integration of that function over that region in three-dimensional space, then what I'm going to have to do is I'm going to have to come up with the bounds, and I'm going to integrate that function times rho squared times sine of theta. So instead of inserting an r like I did in cylindrical coordinates, here I have to insert an extra rho squared times sine of phi. I think I misspoke earlier. That means rho squared sine phi. Rho squared sine phi. We always have to insert rho squared sine of phi when we integrate with spherical coordinates. Now, once again, the order of integration, if I integrate with respect to rho, then theta, then phi, there's a little bit of play in here of which one you integrate with first. And it kind of depends on how your function's written and how your three-dimensional object you're integrating over is. But the key thing is rho squared sine phi. Rho squared sine phi is the thing you have to insert instead of like inserting an R when we inserted in cylindrical. In spherical, we insert rho squared sine phi. Notice that I'm saying that a lot. Rho squared sine phi. Okay? So let's take a look at this. This triple integration is done in spherical coordinates. And if you think about it, we're saying we want to insert a rho squared sine phi. So we're going to insert a rho squared sine phi. This would be like finding the triple integration of d with a 1 as my function here with respect to v. So this triple integration is essentially finding the volume of that object that's within these bounds. Let's go ahead and do that. Let's find the volume of this object that we're integrating over. We can do that using this triple integration. Again, because rho squared sine phi was inserted and the function would have been 1. 1 times dv, and then when we convert, it's 1 times rho squared sine phi with respect to rho, with respect to theta, with respect to phi. So like I said, I'm arguing that this is volume, which it is. So we're going to do this triple integration. Integration first, the outside integration is from 0 to pi. The second integration is from 0 to pi over 2. What I can do, since I'm integrating this first integration with respect to rho, this is the integration of 0 to 6 rho squared times a constant with respect to rho. Integrating 0 to 6 rho squared with respect to rho gives me out a 72. So I end up with 72 times sine of phi. I'm going to now integrate that with respect to theta. And then at the end, integrate that with respect to phi once again. So, whoops. When I integrate with respect to theta, well, 72 sine phi is a constant with respect to theta. So therefore, I can just multiply 72 sine of phi by pi over 2. So I get 36 pi times sine of phi. Integrate that with respect to phi. This is something you can plug into your calculator, or you can not if you want to as well, doesn't matter. But I get the volume here as 72 pi. You can do it by hand, you can plug it in your calculator. Either way, it's pretty quickly done. So this region, this three-dimensional region, has volume 72 pi. Now let's talk about what this three-dimensional region does. The rho goes from 0 to 6. The theta goes from 0 to pi over 2. And the phi goes from 0 to pi. So this is a sphere of radius 6, but the theta value is only going from 0 to pi over 2. And the phi is going from 0 to pi. So this is basically, so theta going from 0 to pi over 2 gives me a quarter of a circle in the XY plane. And if we go from 0 to pi, that takes me from the top all the way to the bottom. So basically, I get a quarter of a sphere. It almost looks like an orange slice of a sphere with radius 6. Let's describe that or graph it. So I'm claiming that the object that we're looking at is this quarter of the sphere, okay? Sphere of radius 6. And I'm claiming that because that theta, again, think of theta in the xy plane, is going from 0 to pi over 2. But the phi goes all the way from 0 to pi. So it wraps around from the z-axis pointing up to all the way down to the z-axis pointing down. And you can think about this using the vector I was looking at earlier. So if we are rotating from, again, theta from 0 to pi over 2, let's make our theta from 0 to pi over 2, we're spanning this circle. So that section, and then allowing my phi to go from 0 all the way to pi takes that entire slice. So we're looking at this slice here as we go from 0 to pi. Hopefully that makes sense. And so we end up with this entire thing. Actually, let me do it this way. As you can see, we're going through and we're just sort of tracing out all of that stuff. Okay, all of that stuff here. And then we fill it in because it's a solid region. So we get that slice, and we're saying the volume of that slice of the sphere was 72 pi. By the way, that object is fairly easy to deal with in spherical coordinates, but with rectangular or cylindrical coordinates, it would be much harder to deal with. Let's do another example. In this example, it says a spherical kickball has a 10-inch outside diameter, and the material that it's made of is a quarter of an inch thick. Now, again, this is careful here. 10-inch outside diameter means it's a 5-inch radius. And the material is a quarter of an inch thick. So let's find the volume of that object. Okay, so spherical kickball, 10-inch outside diameter, that means a 5-inch radius. What's the volume of the material used? Obviously, a bunch of that kickball is just open air. And so if the material is a quarter of an inch thick, then basically the radius on the outside is 5, and the interior radius is 4.75. Again, I'm putting that in there because that's with respect to rho. I should have said volume is equal to triple integration of 1 dV. When I convert that to spherical, d rho, d theta, d phi, then rho goes from 4.5 to 5. Theta is going to go from 0 to 2 pi. That's all the way around the xy plane. And here's the interesting thing. Phi does not go from 0 to 2 pi because since we went all the way around in the xy plane, phi only needs to go from 0 up to 1 pi. Hopefully that makes sense why that is. In the last example, we did a quarter of a circle. We could have done the entire sphere, but if we have 0, if we have a sphere here, let's take a handy dandy vector there. If we go all the way around, let's start at about pi over 2. If we go all the way around, then going from 0 to 2 pi gives us each section of that sphere. So going from 0 to pi gives us each section. If I went 2 pi, I'd go around in the reverse direction and I would trace it from the negative z to the positive z, and that would throw everything off. That would give me some negative integration, and I don't want that. So in other words, as this phi goes, let it go from 0 and stop at pi. And then your theta is going to go from 0 to 2 pi. And if we want to get on this side of the sphere, we use theta to get us there. And we don't use phi. So if I want a spot on this side of the sphere, I could think, well, I'm going to take phi and take it all the way around, but it's a lot easier to do theta from 0 to 2 pi. Take it around. That'll trace all 4 quadrants, and then 0 to pi will get us into the top half and the bottom half. So hopefully that makes sense. So in short, phi only goes from 0 to pi when I'm tracing out that sphere. Now, in terms of doing the actual calculations, this is pretty straightforward because we're going from our first integration goes from 4.75 to 5 with respect to rho. We have a rho squared integrating with respect to rho, and we also have the sine of phi. Sine of phi is just a constant. And we get a pretty ugly fraction, but it's not too crazy. We're going to integrate, from 0 to pi, my outside integral, my second integral goes from 0 to 2 pi. And then when I integrate from 4.75 to 5, rho squared d rho, I get 1,141 divided by 192. And then the sign of phi just stays put. Oh, there we go. Now I can integrate with respect to theta. Now, sine of phi, once again, is constant with respect to theta. So I just multiply by 2 there. And if I multiply by 2 pi, excuse me, multiply by 2 pi there, I'm going to get 1141 divided by 96 times pi. And then the sign of phi, integrate with respect to phi. Okay. If you integrate sine from 0 to pi, you just get 2. So we're going to take 1,141 pi over 96 and multiply that by 2, which gives you 1,141 over 48 times pi, which I guess we can write it in a couple of approximation ways, about 23.77 times pi, or about 74.68. So that's the volume of a spherical kickball whose outside diameter is 10 inches, and when it's made of material that is a quarter of an inch thick. Again, this might seem like a tough integration, but it's a lot easier than dealing with cylindrical or dealing with rectangular coordinates. Let's do one more example with spherical coordinates. Let's use spherical coordinates to find the center of mass of a three-dimensional object. This is going to be the upper half of a ball of radius 3. So it's going to be bounded on the bottom by the XY plane. And on the top, it's going to be bounded by this, which again is just the sphere of radius 3. And we're going to use density function, which is a constant 5. So we're going to have constant density function in this case. So let's go ahead and find the center of mass of the top half of a sphere. Okay, so upper half of a sphere of radius 3 with density function of 5. Now, if you remember, the mass is always going to be the triple integration of the density function over the object with respect to v. And then we also need the moment from the YZ plane, the moment from the XZ plane, and the moment from the XY plane. When you find each of these, we are going to multiply the density function by either X, Y, or Z, depending on which plane we're going from. So if we're willing to deal with spherical coordinates, then what we can do is we can take our density function, which is 5, and in spherical coordinates, this dv changes to rho squared sine phi. Integrate with respect to rho, with respect to theta, with respect to phi. The top half of the sphere, radius is going to go from 0 to 3. If we're doing the top half, then the theta goes from 0 to 2 pi. And if we're only doing the top half, then the phi goes from 0 to pi over 2, because once you hit pi over 2, that's where you hit the xy plane with phi. Okay. So we can do this integration. This integration is fairly straightforward. We're going to take an outside integration, inside integration goes from 0 to 2 pi. And then if I integrate 5 rho squared with respect to rho from 0 to 3, I end up with 45. So I get 45. That sine of phi is just a constant with respect to rho. And then I'm going to be integrating with respect to theta from 0 to 2 pi. That's, again, pretty straightforward because everything there is a constant with respect to theta. And so we're going to get 90 pi times sine of phi, integrated with respect to phi from 0 to pi over 2. And if you integrate sine from 0 to pi over 2, you just get a 1. And therefore, since 90 pi is constant, you just get 90 times pi. So that's the idea in finding the mass, okay? Now, if we do the moments, it's going to look very, very similar to this triple integration, but we're going to have to multiply times an x when I do the moment from the YZ plane. So let's go ahead and do the moment from the YZ plane. We do that same integration, but we'd insert an x here. Now we can't just insert the variable x because x is a rectangular coordinate, but from earlier, we saw that x can be written as rho times sine, hold on. Oh, there it goes. I don't know why I did the P. Rho multiplied times sine of phi multiplied times cosine of theta. So that's what x actually is, all right, in this case. Now we can do the whole thing of integration We can integrate with respect to rho first if we'd like, but I'm going to do that sort of, how do I say? I wouldn't call it a secret, but it's a trick. Since all these bounds are just numerical values, I can switch the order of integration if I want to. So I'm going to go and integrate with respect to theta first. And then I'll integrate with respect to rho. Now, the reason I wanted to do this is because I can take this cosine of theta and integrate with respect to theta from 0 to 2 pi, and all of this is just a constant. 5 times, that's rho to the third, times sine squared of phi. So I guess I can clean that up a little bit. So all of that is a constant. And when I integrate with respect to theta, cosine integrated from 0 to 2 pi with respect to theta gives me a 0. And so therefore, this whole integration just becomes 0. So the moment from the from the moment that's going to give me my x value, the moment from the yz plane becomes 0. Now we're going to do a very similar thing with the moment from the xz plane. What happens is that we insert a y, but y is going to be written as rho times sine phi times sine theta. Everything except for the sine theta is a constant with respect to theta. So I'm going to change my order of integration, and I'm going to integrate with respect to theta first. And this sine of theta integrated from 0 to 2 pi becomes 0. And that means the entire triple integral becomes 0. Again, I chose some nice ones. Now, if only we were so lucky in the third coordinate too. We're not going to be that lucky when we find the z value. So when we're looking at the moment from the xy plane, instead of inserting an x or inserting a y, I insert a z. And if you remember, z is rho times cosine of phi. And so this is what we get. In this case, it doesn't really matter. The order of integration is not going to help me or hurt me or do any of that. But we can see that we're going to get rho cubed times sine of phi times cosine of phi. When I integrate the interior integration, the cosine of phi and sine of phi are constant, so they just stay put. integrating 5 rho cubed with respect to phi from 0 to 3 gives me 101.25. And then again, the cosine of phi and the sine of phi stay put. If I take this and integrate that with respect to theta, well, everything's just going to get multiplied by 2 pi because cosine phi, sine phi stays put. Oh, I should have. And so what I'm going to get is 202.5 times pi times cosine of phi times sine of phi. Now, if you want, you can do this by hand. It's just a trig integration by hand. It's not too crazy difficult, but you can also do it with your calculator. You end up getting 101.25 times pi. So that's what I ended up with. Center of mass is always a three-dimensional point. The first coordinate is given by the moment from the YZ plane divided by the mass. The second coordinate, the Y coordinate, is the moment from the XZ plane divided by the mass. And the third coordinate, the Z value, is given from the moment from the XY plane divided by the mass. In our case, those first two moments are 0, so we get 0 divided by anything. Well, if you remember way back when the mass was 90 pi. So 0 divided by 90 pi is your x value. 0 divided by 90 pi is also your y value. And your z value is 101.25 pi divided by 90 pi. And if you simplify that, 101.25 over 90 gives you 1.125. So there we go. There's the point, which is the center of mass. Now, the actual thing we're finding the center of mass of is this sphere whose density function is 5. So center of mass of that sphere, it's going to be a solid half of the sphere. So it's the upper half of that sphere, solid with density of just constant of 5. Obviously, if we have a point, that point that's the center of mass is going to be somewhere in here, which obviously it is. It's hard to see, so I'm just going to use the shell of that sphere and look underneath, and you can see the center of mass sitting there at that point in space. And the height of that point is at 1.125. So that is the center of mass. of, again, sphere of radius 3. You can imagine it's not going to be halfway up. It's not going to be at 1.5 because there's more stuff on the lower half of the sphere than on the upper half of the sphere, the upper half of the half sphere. So hopefully that makes sense. So in this video, we saw how to use the spherical coordinate system and saw how to integrate using the spherical coordinate system. We also earlier saw how to integrate using the cylindrical coordinate system, which was just an extension of the polar coordinates in R2. Spherical coordinates is also an extension in R2, but in a different manner, different from R2, but in a different manner. So we used spherical and cylindrical coordinates in helping us do our triple integration. So that's the end of this video on triple integration using cylindrical and spherical coordinates.